Well, welcome back, everyone, and thanks for coming. Remember, what we're talking about is screening. Screening involves using a test to try to detect disease before it becomes symptomatic during a detectable preclinical phase. Now, in the last lecture, we talked about the desirable properties of a screening test. We want a test that's accurate, that has high sensitivity and high specificity in order to classify people as being likely or unlikely to have this disease in a correct way. We also want to have a disease that's painless, not very expensive, and doesn't have any side effects that could be harmful for individuals. But all that talks about the screening test. Now let's talk about a screening program, which involves giving a test to a specific population for the purposes of detecting disease. So let's talk about now what screening programs are suitable, meaning what tests given to what populations would be appropriate for detecting disease. Well, first of all, what a screening program means using a test in a specific population. How can we measure whether that process of using this test in a specific population was beneficial? What are the process measures that we can say that this screening program had value to it? Well, one process measure we could look at is how many people just get screened. If I have a great screening test, say radiation for mammography for detecting breast cancer, but no one undergoes that test, then my screening program has failed. Even though I have a very accurate test, if no one undergoes it because of the discomfort of the mammogram, then I'd have to say my screening program has failed because no one is undertaking the opportunity to be screened. Well, what's another process measure that says this program has some merit to it? Well, one thing to do is how many cases of breast cancer are detected in the preclinical phases. How many of these women who come to my screening center to have mammograms actually have a test that labels them as being likely to have a disease and later on turned out to have the disease before the symptoms developed? Those are the benefits of the screening program, to detect cases of disease earlier. So counting the number of cases that exist is going to be very valuable. Now, that number is going to depend on how much disease exists in a population that's being screened, how much detectable preclinical breast cancer exists in this population. That's going to be a determinant of how many cases I detect. Another process measure that talks about the suitability of a screening program is the cost of the test. A test that's very inexpensive is going to allow me to screen many, many more people with a fixed budget than a test that is very expensive. So the cost of the screening test and the program, which involves recruiting people to be screened, is something to take into account. And then finally, maybe the most important thing to measure in terms of process of a screening program is the outcomes. When I follow up these people who are screened positive, how many of them are going to be classified as really have the disease? Those are the cases that were detected prior to symptoms developing. Those are the ones I'm trying to aim at this screening program. Well, what sort of measures can you use to quantify those outcomes that we just talked about? In terms of the accuracy of the screening test, we talked about its sensitivity and specificity. We can also talk about two other measures that talk about the impact of giving this test to this specific population. We can talk about something called the positive predictive value, or the predictive value positive, or the negative predictive value, although some people refer to it as the predictive value negative. The positive predictive value is the proportion of people who ultimately get diagnosed with the disease among those people who are tested positive. So imagine you having a screening program giving mammograms to women who don't have any signs, any symptoms of breast cancer. A certain number of them are going to be tested positive by the screening test. You're going to follow these people up. You're going to be treating them for breast cancer. You might also, before you do that, might give them other tests, more invasive tests to see if they really do have breast cancer. But the percentage of people who actually get diagnosed with breast cancer among those people who were tested positive is what we call the positive predictive value. The chances, the probability of having the disease, given that your test was positive. We'd like that to be high. We can also talk about the negative predictive value. Among people who are tested negative, women undergo mammograms, they're negative, they have no additional follow-up. We're hoping those people are free of disease. Some of those people might get diagnosed days later, weeks later, months later as having breast cancer. Those are the people we missed. What we'd like to have is, in a good screening test applied to a population, is that most of the people who are tested negative end up not having the disease. So the negative predictive value is the proportion of people who don't have the disease among those who are tested negative. So positive predictive value and negative predictive values are good measures of the performance of a screening test in a specified population. They're good measures of a screening program. But there are others to look at. What are other indications that this screening program has value? Well, we can look at the people who have breast cancer detected by screens. And we could look at the stages of those breast cancers. Remember, the stage is a marker for the invasiveness of this disease. A stage 1 breast cancer is less invasive than a stage 2 breast cancer. So hopefully screening tests are detecting diseases at earlier stages. So what we can do is look at the stage distribution of the disease among those people who were tested positive and later diagnosed as having breast cancer from the screening program. And a distribution of mostly early stage disease is a good marker of a good screening program. The other thing we'd like to have is, hopefully by detecting these cases of breast cancer early and treating them early, we are avoiding what would have been maybe a fatal disease if we waited until the signs of symptoms develop. So another good measure of a screening program is the fatality rate, the number of deaths out of the number of people who get diagnosed with the disease from a screening program. We'd like to have a very small fatality rate, a very small proportion of these people dying, or at least having them die later than they normally would have died if they had not undergone the screening program. So these are process measures we can use to describe the advantage or the merits of a screening program. Well, let's just talk about the top two, the positive and negative predictive value. Well, here's that screening program we talked about before when we talked about sensitivities and specificities for the mammogram. Remember, before, the sensitivity was about 75%, the specificity was about 98%. Now let's use those same data to talk about the predictive values of these test results, the positive and the negative predictive value. So the positive predictive value says, let's look at everybody who was tested positive by this mammogram. There are 1,115 women. And say what percentage of them actually ended up having breast cancer. Well, these 1,115 women which were tested positive probably underwent further testing, maybe more invasive testing, were followed up over a period of time, and it turned out 132 of them were ultimately diagnosed as having breast cancer in the detectable preclinical phase. So 132 out of 1,115, or 12%, is what we call the positive predictive value. It's the chances of having breast cancer given or if you had a positive test. The negative predictive value looks at the people who had negative tests, 63,695, and asking how many of them were disease-free, meaning no signs of breast cancer at the point of time when the screening was done, based on information that was gathered later. And as best they could say is 63,650 of those women were free of disease. So the negative predictive value is the 63,650 divided by the 63,695, or almost 100%, 99.9%. That's the positive and negative predictive values. Now, Marcello spent time, when he talked about screening tests, and talked about sensitivity, specificity, positive and negative predictive values, talking about the relationships between, say, the positive predictive value, the 12% in this case, and the sensitivity and the specificity of the screening test. And he mentioned the role of Bayes' theorem to describe how the sensitivity and the specificity impact the value for the positive predictive value. Well, you can write Bayes' theorem in a number of ways. This is the easiest way to remember it, at least from my point of view. It talks about the odds of having disease, not the positive predictive value, which is the proportion, but the odds of having disease among people who had tested positive. So if I go back to the previous slide, and I look at the 1,115 people who were tested positive, 132 of them had breast cancer based on some additional follow-up, and 983 did not. Remember, the positive predictive value is the proportion of people among those people tested positive who actually have breast cancer. we can talk about the odds of having breast cancer. The 132 divided by the 983. In terms of Bayes' theorem, that's mathematically, going back to the next slide, the positive predicted value divided by 1 over the positive predicted value, or the odds of having disease given you have a positive test. And what Bayes' theorem says is the odds of having disease if you have a positive test is equal to the product of two quantities. First, it's the odds of having disease in general in the population. So if I go back to the previous slide, in the entire population of 64,810, 170 people have the disease, and 64,633 don't have the disease. 177 divided by 64,633 is the odds of having disease in the population, not taking into account whether there was a positive test or a negative test performed, observed on these people. That's what we call the prior odds of having disease before we give the test. And what Bayes' theorem says is that the posterior odds, based on having a positive test, is equal to the prior odds times something which we refer to as the likelihood ratio. The likelihood ratio is the sensitivity of the test divided by 1 minus the specificity of the test. Okay, so what's a good test? A good test, remember, has high sensitivity and high specificity. High sensitivity means the value for the sensitivity is close to 1. High specificity means the value for the specificity is also close to 1. Therefore, 1 minus the specificity would be close to 0. Remember what we talked about before about dividing by 0. Well, if you divide by 0, you get infinity for an answer. So if you divide by a small number, if 1 minus the specificity is 0.01 or 0.02, meaning the specificity was 99% or 98%, that means for a good screening test, this likelihood ratio is going to be big. You're going to be dividing a sensitivity that's close to 1 by a value for 1 minus the specificity, which is close to 0. When you divide by 0, you get a big quotient. So a good screening test is going to essentially multiply the prior odds, which doesn't take the screening test into account at all, by this likelihood ratio to give you what the impact of the screening test would be in that population. How much it would change a person's risk of having disease from incorporating into it the knowledge that the test was positive. So a good screening test will lead to a high posterior odds of having disease. But notice the posterior odds also depends on the prevalence of disease in the population. So as Marcello mentioned, one way to improve the yield of a screening program, in other words, to have high positive and negative predicted values, is to use a test that has high sensitivity, high specificity, in other words, has a high likelihood ratio, but also apply it to a disease, to a population where the detectable preclinical disease has a high prevalence, where the prior odds of disease is a big number. So there are two ways to make the posterior odds from a screening program high. One is by using a test that has high sensitivity and high specificity. The other is to make sure you apply it to a population where there's a lot of preclinical disease to be found, a high prevalence of preclinical disease. And those are the two features that make the screening program look very good. Using a good test, high sensitivity and high specificity, and marketing it or giving it to a population where there's lots of preclinical disease to be detected. If that's the case, the screening program is going to be a hit. You're going to have high predicted value positives and high predicted value negatives as a result of your screening test. So what are the implications? As I say, the positive predicted value depends on the prevalence of disease in the population. It also depends on the sensitivity and the specificity of the test. So screening in a high-risk population will yield high values for positive predicted values. How can you screen in a high-risk population? How can you anticipate that your screening population will contain lots of preclinical disease to be detected? Well, one way of doing that is to have essentially a pre-screen. If I think breast cancer is more commonly found among older women, then don't waste my time by screening young women for breast cancer. only enroll women in my breast cancer screening program who are above a certain age, and that's why there are clinical guidelines that recommend screening only be done in certain populations. And for breast cancer, they recommend it be done only starting at a certain age in a woman's life. The reason for that is to give you a screening population with enough cases of detectable preclinical breast cancer to be found by your screening program. That's the way to enhance the yield of your screening program. The other thing that we should talk about, and we will in a future lecture, is how often do we screen? Do we screen women every year? Do we screen women every 3 months, every 6 months, or every 3 years? What's the best frequency? Because once you screen a population, you'll detect preclinical cases. If you screen them the next day, chances are there's no additional preclinical cases to be found. The only new cases were those who became preclinical cases in the last 24 hours. So we want to wait long enough for more new cases of preclinical disease to enter a population before we screen that again. But we don't want to wait too long. If we wait too long, some of those preclinical cases will move in to become symptomatic and will become clinical cases, and we've missed the window of opportunity for detecting those cases earlier. So the screening frequency is something to consider. And what we want to screen is not too soon to be looking at populations with very few new cases of preclinical disease, but not also too late to miss the opportunity of catching cases before they became clinical in their stages. So that's what I wanted to say about screening programs. Now the next thing I'd like to talk about in the next 2 lectures is how you evaluate a screening program. How do you determine whether the screening program has some merit? Not only in terms of its predicted value positives and things like that, but really does it have some advantage? Does screening with a test in a population, is it better than not screening at all? Does it justify the cost, the discomfort, the time involved in launching a screening program? That's what we'll talk about next time. See you then.